Just start recording. Now, as if it wasn't bad enough that during class on Tuesday I had quite a few technical difficulties, I had a little bit more after class, and as a result, anything that I had typed in to my notes during class was lost and didn't make it to file that was posted on Canvas. I am working on rectifying the situation. And hope to fairly soon. So in general, the way it's going to work is that whatever I type in here, that's what I'll post in Canvas. So that's what happened on Tuesday was an exception. Now, I have far too much material in these notes to expect to cover in one day after being behind after Tuesday. So I'm just going to get as far as I can through this. I'm sure I'll catch up at some point later, but not necessarily today. Okay, so last time I introduced a scalar product of functions as a generalization of the dot product of ordinary vectors in Rn. And when I say ordinary vectors, that's what I mean, like the kind of vectors you dealt with in calculus. And from the idea of scalar product, the concept of a norm that measures the magnitude of a function. Actually, that's what I'm going to cover right now. So, with vectors in Rn, you have a notion of the magnitude. You take the square root of the sum of squares of all components, and that gives you magnitude. That's also known as Euclidean length. So we want to be able to take the magnitude of a function f of x as well. And just as we had a natural adaptation of the concept of the dot product of vectors to scalar product functions, we'll be able to do the same thing in going from a norm of the ordinary vector to the norm of a function. So here is a definition of a norm. And a norm can be applied to any vector space. So the input to the norm is a vector from whatever vector space you have, whether it's ordinary vectors, functions, and function spaces, doesn't matter. But the output is always a real number. So, and that's necessary because we're trying to describe the magnitude of whatever kind of vector you have. And to describe magnitude, we just want a number. But not just any function that maps vectors to numbers can be a norm. There are certain conditions that it should satisfy for it to make sense as a notion of magnitude. This one's particularly important. Magnitude should always be non-negative. It doesn't make sense to have a negative number be the magnitude of a vector of any kind. So the norm of v is always greater or equal to 0. Furthermore, the only time it should be 0 is if you're taking the norm of the 0 vector. Whatever constitutes the 0 vector in your space, the magnitude of that certainly should be 0. But the magnitude of any other vector should be positive, strictly positive. Also, we have the operation of scalar multiplication of vectors, and it helps define a vector space. If you scale a vector, then that should scale the magnitude. So if I take a vector and scale it by 2, for instance, then its magnitude should be doubled. Notice it's the absolute value of the scalar. So if I take a vector multiplied by -4, well, the length of that, the magnitude of that vector should be increased by 4. And then, just as for absolute value, we have triangle inequality. The magnitude or norm of the sum should be less than or equal to the sum of the norms. So any function that you can conceive of that satisfies all three of these properties for a given vector space, that is a norm on that space. But that would be nice to have a specific norm that we'll make use of. And you can define the norm in terms of a scalar product. So this is the norm that's induced by scalar product. You take the scalar product of the vector b with itself, and then take the square root of that. And in fact, we have this already for ordinary vectors. If the scalar product in question is the dot product, then the dot product of a vector of itself is the Euclidean length of that vector squared. So we already have an example of that here. You see before. Okay. One thing we need to be careful about with functions, though, is that a function space, as opposed to ordinary vectors, you may have a situation where, for certain norms, the function f might be non-zero at isolated points. For example, suppose you have a function that's equal to 0 everywhere, except at one single solitary point, it's equal to 1. Certain norms of that function space still turn out to be 0. So that's something to be mindful of. But that only happens if, under this circumstance, f is non-zero on a set of measure 0. Informally, what's meant by measure 0 is that you're talking about a set of points that has no volume in the space. Like if you're in one-dimensional space, a single point along the real axis, that set has size 0, because whereas as opposed to an interval, like give the interval AB, that has a non-zero size, or volume in one dimension. It's B minus A. So that would be a set that has non-zero measure, but a point by itself has measure 0. So as long as f is 0 everywhere, except possibly on a set of measure 0, the norm can still be 0. No Microsoft Office, I don't want to update anything with them up. Okay. So now to define a function space, a Hilbert space that is equipped with a scalar product and a norm based on that scalar product. So a norm defined using this equation here. And this is an important criterion for it to be called a Hilbert space. The space has to be what's called complete. Now, what do I mean by complete? It means that any function in the space whatsoever can be expressed using some basis. As it could be an infinite basis if need be, but so as long as you have a function space, a scalar product defined in that space, the norm induced by that scalar product, by this, and completeness, that is a Hilbert space. So not all function spaces are Hilbert spaces. There's really a hierarchy. Like you can have function spaces, you can have normed spaces, and then this falls within, this is a proper subcategory of that. So another way of putting it is that the space has a basis, and the span of that basis, instead of all possible linear combinations of these basis functions, is the entire space. There's nothing left out. So I'll give an example of a Hilbert space. Space I mentioned last time, P3. All polynomials of degree at most 3. And we'll work on the interval -1 to 1. So this is our scalar product. So integral from -1 to 1. And the first function f is conjugated. So don't forget that. If you allow the functions to be complex valued, you have to remember to conjugate. And then, so here's some examples of inner products. We're not using weight function is just one. So here I'm defining polynomials, L0 is equal to 1, L1 is equal to x. So here I'm taking scalar products of these functions. Here, function 1 with itself, and then x with itself, and then 1 with x. And one thing I want to point out is, because the interval is symmetric around 0, the interval is -1 to 1. An integral from -1 to 1 can be expressed as an integral from 0 to 1. In the case where a function is odd or even. So here our integrand is 1. Here integrand is x squared. Both of those are even functions because you have x raised to an even power. And when you have an even function like that, the integral from -a to a can be written as twice the integral from 0 to a. But if you're working these things out by hand, I'd recommend doing that because it reduces the possibility of sign mistakes. And notice we get a positive result in both cases, which makes sense because if you're taking the inner product of a non-zero function with itself, that's the magnitude squared. It ought to be positive. Whereas here we have an odd function. So we have an odd power of x, integral from -a to a. That's always going to be 0. So we can just jump to that conclusion directly without going to trouble evaluating the integral. So these are properties that I use in quickly evaluating these for even and odd functions. So you would have learned about this in Cal 2, but I figured that reminder would help. Any questions up to this point? Okay. For this scalar product and this norm, or actually really just any norm induced by a scalar product in this form, there's a helpful inequality called the Cauchy-Schwarz inequality. That comes into play in improving various things. And this is the inequality that if you take the scalar product of two vectors f and g, then an absolute value is less than or equal to the product of their norms. So it's not something that necessarily holds for norms in general, but it does hold for any norm that's induced by a scalar product. So I'm going to give the main ideas of how this inequality can be proved. Because we kind of won't go through every single little detail, but it's something you can. But they're all written here, and you can examine later if you like. Now, I'm going to simplify the proof a little bit. We're going to assume that f and g are real valued functions. Because if you allow them to be complex, it does complicate the matter some. And if someone really wants to know, I can explain a number of times how it's worked out. But the general idea is the same. Okay. So what you can do is you can let C be any scalar. And we're also going to assume that G is non-zero, because if both functions were 0, then you'd have 0 on both sides of the inequality, and this whole thing would be trivial. So we're going to assume at least that G is non-zero. Well, the scalar product of any function with itself must be non-negative because, whoops. Actually, I'll explain why. This is the same as the norm of f minus cg squared. By the definition of a norm is equal to this. The norm must be non-negative. So we have this. That's one of the main ideas. We're going to use this property. Now, here's something that's important to be aware of. That you can, using the distributive properties of a scalar product, that this scalar product with each function, each operator having two terms, can be broken down into four separate scalar products. Basically just multiplying it out. So using this distributive property, you get these four inner products, or scalar products. Well, they are inner products, but we're both likely to use the term scalar product. And then these constants can be pulled out of the inner product. So these two terms actually end up being the same, because you can pull out the c for one thing, but also when f and g are real, the scalar product is commutative. So f scalar product g equals g scalar product f. So these terms combine. Here I pulled out the c again, and I get c squared. The other property, actually, literally every property I gave on a scalar product last time is being used right here in these few steps. The scalar product of any function of the vector of itself is the norm of that vector squared, so that's used here and here. So now, if you think of this whole expression as a function of c, so f and g are considered constant in the first case. The idea is to find the minimum of this. So if you take the derivative of this, the whole expression with respect to c, then you get, this is what you get. And since we're trying to find the minimum, we're going to set that equal to 0. I should mention, if you took the derivative of this, in other words, the second derivative of the original, you would get 2 norm of g squared. That's positive. So that tells you that whatever critical point you're going to get is going to be a minimum rather than a maximum. So then you solve this for c, and you get this. And now we can take the value of c and substitute it back in here. So I go ahead and do that, and after a bit of algebra, this is what you get. And since we knew all along that this is greater than or equal to 0, we can just rearrange this and take square root of both sides of the band as opposed towards inequality. Yes?
What happened to the integral of the magnitude of f squared from both?
Oh, wait.
I don't think I got the integral of like negative 2c, and what did you do with the magnitude of f squared on top?
From here
Yeah.
to here? Oh, we're thinking this is a function of c. That means this term is a constant. You have a question? What happened here? If you allow f and g to be complex, what we need to do is assume that the constant, the scalar c has a certain form that involves a complex exponential, and then you can do all of this. But yes, we need to be careful about this. Certain conjugates get in there. It's a mess. Okay. Now, as I mentioned last time, in something that you would have seen in calculus, you have two vectors in Rn. They're called orthogonal if their dot product is equal to 0. So similarly, if we have two functions in a Hilbert space, and if their scalar product is 0, then we say that those functions are orthogonal. Now, it doesn't carry the same geometric meaning as the case of vectors in Rn, because vectors in Rn are orthogonal. You can see, if you were to visualize them, you'd see that they are perpendicular. Now, we don't have any geometric meaning like that in this case, but their being orthogonal is still very useful, as we'll see in a bit. And here's how. Suppose you have a Hilbert space, and it has some basis, functions phi 1, phi 2, and so on. That could be infinite. It just depends on the Hilbert space in question. And if it's known that the functions in your basis are all orthogonal, that means the scalar product of any two distinct functions from this basis are 0. And we'll see functions like that. Like for certain spaces, you can have sines and cosines that are orthogonal. Or later we'll learn about certain families of orthogonal polynomials. So orthogonal functions are not hard to come by. So if the basis satisfies the condition that it's an orthogonal set, and then I want to describe any function in my Hilbert space in terms of that basis. So it's a linear combination of these basis functions. I want the coefficients an. So at this point, these coefficients are unknown. Now, normally, if you just have any old basis, finding these coefficients could be quite difficult. You may have a system of linear equations to solve. But things simplify considerably when the functions are orthogonal. Here's what you do. You take the scalar product of both sides of this equation with one of your basis functions. So I choose phi k. Notice the index needs to be different from n. So the left side I have a scalar product of phi k with f. Then the right side I have a scalar product of phi k with this whole series. But now I can use properties of the scalar product. So a scalar product with a sum can be written as the sum of scalar products. An is a scalar, you pull it out. So now what I have is this sum of coefficients times scalar products of functions that are orthogonal to one another. All of these are 0, except for when n is equal to k. So all of these terms vanish except for the kth term. So this infinite sum reduces to this. So now I have this equal to this. I can just rewrite this and solve for ak. So here's my general formula for the coefficients an. It's a scalar product of each orthogonal basis function with f, the function you're expanding, divided by scalar product of that basis function with itself, which is guaranteed to be a strictly positive number. The point is, you can compute each coefficient independently of the other ones. So if you have a computer doing this, you can do it in parallel, for instance. So a whole lot less work than if a basis was not orthogonal. Questions about how this formula was arrived at? Now I'm going to take orthogonal basically one step further. You remember from calculus, if you have a vector in Rn, and if its magnitude is 1, called a unit vector. Now, if you have any old non-zero vector that's not necessarily a unit vector, you can make it a unit vector by dividing by its norm, its magnitude. So b over norm of b, that's a unit vector. So you can do the same thing with functions in a Hilbert space. I can divide a function f by its norm. And so we say, we don't call it a unit vector necessarily, but we say that the function is normalized. So what if you have an orthogonal basis, and then you normalize each of your basis functions? Then this denominator here would be 1. So then computing in coefficients is even easier, just one scalar product to compute. And that leads to what's called an orthonormal set. So an orthonormal set is a set of functions that is orthogonal. So the scalar product of any two distinct functions from the set is still 0. But the scalar product of any one of these functions with itself is 1. This leads to this notation, delta ij, that's equal to 0 if I not equal to j, 1 if I equal to j. It's called a Kronecker delta. You may have seen this like in a linear algebra course. It's a very convenient notation to express a quantity that's usually 0, but under certain circumstances is equal to 1. For example, it can be used to describe the identity matrix. So that's the idea, is that each one of these, oh, I have the wrong Greek letter here. In LaTeX, there's two forms of the Greek letter phi, and I used the wrong one. So let's fix that. Okay. So all you're doing is you're taking an orthogonal basis, and you normalize each of the functions in it, and it's orthogonal. So as an example, suppose we're working on a Hilbert space of functions on 0 to pi. These functions, sine nx, where n is an integer, these functions are actually orthogonal. So if here's our scalar product, so no weight function, the weight function is 1, and we have integral from 0 to pi. If I take the scalar product of two of these sine functions, so sine mx or sine nx, then so I can write out what that is, and then I use what's called a product to sum identity. So it's one of your trig identities that you've probably forgotten. I forget those all the time too, so I just write them again. Then this is written in a form where it's possible to integrate. And when n is not equal to n, you end up with 0. So that means that these functions are orthogonal. So in other words, these functions form an orthogonal basis for the Hilbert space. But what if you want to normalize them? So in that case, you need to compute the scalar product of each one of these with itself. So to do that, okay, so here's the integral you get in this case. Here you use a different trig identity. It's called a half angle identity to be able to integrate that. And you end up with pi over 2. So that's the inner product of sine nx with itself on 0 to pi, and for any such n. So now we know how to normalize our orthogonal basis functions to get an orthonormal basis. So if I divide by the square root of this, I get these functions. These are orthonormal. So all I'm doing is just scaling them the way that I need to. So now I have a function f of x, but I want to expand in this orthonormal basis. I want these coefficients an. All I have to do is take scalar product of each of my orthonormal basis functions with f. And then I have my coefficients, because they're already normalized. Questions about this example? Okay, and we call it a Fourier sine series. So when you expand a function that's a linear combination of infinite basis of sines, that's a Fourier sine series. So you would have seen a lot of that, for instance, in our PDE class, math 417, 517. Okay. Now, another thing I want to point out about these kind of expansions in an orthonormal basis. So if you have two functions f and g that are expanded in the same basis, so they just have different coefficients, so an in this case, and bm in this case, that leads to an alternative way to compute the scalar product of the functions themselves. So if I want to take the scalar product of f and g, so I go ahead and fill in their expansions. And then I use the properties of the scalar product. So summations are pulled out. These scalars are pulled out. Notice the one here on the left, an, I take the complex conjugates. Don't forget to do that. So now I have this double summation, but look at the scalar product I have here, phi n with phi m. Well, these functions are orthonormal. So those are equal to 0 when n is not equal to m, and they're equal to 1 when n does equal to m. So that leaves this Kronecker delta here. So how I make use of that is to make the inner summation go away, that all of these terms are 0 unless m is equal to n. So I'm just going to set m equal to n throughout this expression. And the inner summation goes away because n is only assuming the specific value. So this is what I get. But this is a dot product, as an infinite dot product, of the coefficients of f with the coefficients of g. So, that if I think of a as a vector of coefficients, and b also as a vector of coefficients, so the scalar product becomes a dot product. And this could be very helpful in certain situations. For example, like if you have functions expressed as Fourier series, whether it's a sine series or cosine series or a full Fourier series, you can take the scalar product of two functions as either in physical space, like you leave them as functions of x and you form the integral, or you take the dot product of their respective Fourier coefficients treated as vectors. You can take the scalar product in two different ways. And for Fourier series in particular, that's useful in a number of situations. For vectors, the star needs a adjoint. Okay, yeah, sorry, I need to do this definition here. When you have a vector, so vectors are normally assumed to be column vectors. The star is called a Hermitian transpose. So you take the transpose of a column vector, which makes a row vector, but you also take a complex conjugate. So that's what Hermitian transpose means. And here's some other ways in which a Hermitian transpose is written, in case you come across it elsewhere. The Hermitian transpose is important because in various concepts that make use of a transpose of a vector or matrix, when you're talking about real valued vectors and matrices, if you want to generalize that, whatever it is, to the case of complex vectors and matrices, generally the transpose has to be changed to the Hermitian transpose for the whole thing to work. So, if you just leave a transpose as it is, it might fail in the complex case. For example, dot product. Okay, dot product with real vectors, when you learn in calculus, you multiply corresponding elements of a vector and add them all up. Well, that is not a good idea in the case of complex vectors. You should take the complex conjugate of one of the vectors. And the reason for that is, if you don't do that, then if you try to define like the magnitude of a vector as the square root of the dot product itself, you can get you can end up with a improper value of the norm. It could be negative or imaginary. That's why the complex conjugation is needed. Because that one property of norms, that norm must be a real number, it must be non-negative real number. That's violated if you forget to take a complex conjugate. Okay. And here's another interesting fact that comes out of this relationship between scalar products and dot products and coefficients. If you let the two functions be the same, so the norm of f squared is scalar product of itself, but then based on what I just did, that's the sum of the absolute value squared of all the coefficients in the basis expansion. This is called Parseval's identity. Normally, Parseval's identity is described in terms of Fourier series, that the norm of a function is equal to the sum of the norm of a function squared is equal to the sum of squares of all the Fourier coefficients. But it applies with any orthonormal basis expansion. Okay, so here's an example involving cosines. So these functions form an orthonormal basis with respect to this scalar product, again on 0 to pi, but now we're doing cosines instead of sine. Those normalization is the same, square root of 2 over pi, except for this one. So the norm of constant function on 0 to pi is pi instead of pi over 2. So now, suppose I have these two arbitrarily chosen functions in my Hilbert space. So what I want to do is express these functions in terms of my orthonormal basis. So that would involve taking scalar products with these basis functions. Okay. So it turns out that if I take the scalar product of psi 1 with each of these, then I can get the coefficients of this function in this basis. And these are what the coefficients turn out to be in the two cases. So then, suppose I wanted to compute scalar products of these functions. I could have done it directly. I could just multiply these two together, or multiply this with itself and this with itself, and go ahead and evaluate the integral. But I don't have to do that if I have these coefficients already. So the scalar product of psi 1 of itself, I can just take these coefficients, take the sum of their squares, and that's the scalar product right there. Same with psi 1 and scalar product of psi 2. I can take this coefficient times this one, plus this coefficient times this one, and then this times this one. This one doesn't have a phi 3, whereas this one does. So the coefficient of phi 3 of this function is 0. So I would not include this. And then you can see here there's a 0 here. So, wait. Oh, typo here. This should be psi 2 of itself. So here I'm using Parseval's identity to evaluate scalar products this way instead of actually evaluating the integral. Shows you the length to which baptisms will go to avoid evaluating integrals. Questions about this example? to tell you about Bessel's inequality. Now, suppose I have a function that is not necessarily in a Hilbert space, but even if it's not a member of a Hilbert space, I can still try to take its expansion in some orthonormal basis for that Hilbert space. It's just that this function here that I get would not necessarily equal f of x itself. So that's what I would point out. Like, the Hilbert space itself is complete. All functions in it can be described by this, but maybe your function f doesn't belong to it. But even though f is not in the Hilbert space, I do have this inequality. Now, if f was in the space, this would actually be an equality. That'd be Parseval's formula. But in the case where Parseval's identity does not apply, because it's not in the space, I still at least have this inequality. Oh yeah, one thing I want to point out. It may seem redundant to have absolute value and squared, but we're talking about coefficients that are not necessarily real numbers. It could be complex. That's why I have that. It's actually a homework problem to prove Bessel's inequality. So I won't go through the whole thing here, but I can get you started at least. But use this starting point. That f minus the expansion, take the scalar product out of itself, take scalar product of any function with itself. And you have something that is non-negative. And so you can take advantage of that to establish Bessel's inequality. But one thing I want to point out, even though I've written it like this, for the sake of the homework problem, what I'll suggest is that for this summation, use a different letter for the index. So like n over here and m over there, because you're going to be mixing sums up, and you'll want a different index for that. Okay. If Bessel's inequality actually is inequality for a particular function f, we say the expansion converges in the mean. But again, as I mentioned before, it may not agree at certain select points, like a set of measure 0, but generally it will agree in that case. And now I'll give an example of that. So here's a function as f(x) equals x, and we're working on the interval minus pi to pi. And I want to express this function in terms of sines and cosines. So because these functions are all orthogonal to one another. So I'm going to have an expansion of this form. So I have the coefficients an that go with cosines, including the case of n equals 0, because cosine of 0 is 1. And then also the coefficients bn corresponding to the sines for n equal 1, 2, 3, and so on. Now, f(x) equals x is an odd function. Cosine is always an even function. If I take a scalar product of x with a cosine on an interval minus pi to pi, an interval that's symmetric around 0, I'm going to get 0. The interval of an odd function. The even function times the odd function is an odd function. So I can conclude right away that all the an's are 0. Like get that out of the way with it. So really I'm going to get f of x as the sum of sines. So here are my coefficients, because the sines are orthogonal, not orthonormal, just orthogonal. So I can bother to normalize it. So here's my general formula for coefficients. Scalar product with f divided by scalar product with itself for each basis function. So I define what that is. The integral of scalar product of sine and x with itself is going to be in this case, it turns out to be pi, because I'm on the interval from minus pi to pi. So it turns out to be the length of the interval divided by 2. So that's what leads to this, and I have to divide by that. So that's why I have this factor of 1 over pi here. So this integral comes from the numerator. I'm not sure why I switched from x to t in here. I didn't need to do that, but sorry for any confusion that causes. Right, but anyway, you work out the integral, and what you get is this. So we get 2 over n if n is odd, and minus 2 over n if n is even. So I go ahead and fill in that expression into my sum. So now this is my expansion for x. Oh, I go there. No, I don't. Okay. So now I want to take a look at this. So here I've visualized what that expansion looks like when I have to cut off n at a certain point. So at n equals 5, n equals 10, n equals 20, n equals 40. And we see, and it's going to be an approximation to f of x equals x no matter what. But look what happens as n increases. On the one hand, in the interior of the interval, it is getting closer to f of x equals x. But look what's happening at the boundaries. We're having these high frequency oscillations. So what's going on with that? The problem here is that if we take f of x equals x and taking its 2 pi periodic extension, so you take a graph of x on minus pi to pi and you just keep repeating that. Well, that has a jump discontinuity at any odd multiple of pi. And what ends up happening is that the series expansion, look at the curve here. It's hovering around f(x equals x), but then it goes up towards 0. Here again, it's heading up towards 0, and it's still kind of doing that. So this series that we have here, when x is equal to plus or minus pi, or any odd multiple of pi, will actually not converge to x. It will converge to 0. Because it's the average of the two values on either side of the jump. So whenever the periodic extension of your function has a jump discontinuity, they have different values at the endpoints, it's not periodic, then this series converges to the average of those values on either side of the jump. So that's why it's converging to 0. But at every single point in between, it's going to converge to f of x equals x. So that's why you have this troublesome behavior here, that on the one hand, when it converts to this, on the other hand, also when it converts to 0 at these points. So you get these oscillations that are called Gibbs phenomena. So that's why it's a big problem to approximate non-periodic functions by Fourier series, because we end up with the jump discontinuity that cannot be resolved accurately by Fourier's truncated Fourier series. So you have substantial errors in your approximation near these discontinuities. Works great in the interior, but at the boundaries, not so much. So that's something that's unfortunate. Questions about what happened with this example? Here's something that's from mathematical physics. Dirac notation. So it's a way of representing vectors in function spaces. So a way to describe a function in Dirac notation is using the part of the scalar product notation. You have a vertical bar on the left and then a right angle bracket to the right. So it's like half of a scalar product. But the complex conjugate is written as the other half of a scalar product. So you have a left angle bracket to its left, vertical bar to its right. And so the way these are named is to take the word bracket and assign one half of that word to each entity. So the left one, that's the conjugate, is called a brat. And the right half is called a ket. Kind of weird, but I'm a physicist, so what do you expect? Sorry to any physicists who are listening. So you put them together, and then one vertical bar is removed because it's redundant, and you get a scalar product. So the brat and the ket come together, bracket, and there you go. I don't make this up, I just report it. So now, using the ket notation, I have a function in Hilbert space, and I'm expanding it in an orthonormal basis, so each member of the orthonormal basis is also expressed using the ket notation. So it was written as an expansion with coefficients aj, but the coefficients aj have this formula here, this scalar product. But then what you can do is take this ket here, the one for f, and factor it out because it doesn't depend on j. So because you're able to break up scalar products, you're allowed to do this. So here, instead of a scalar product where you have a brat followed by a ket, now you have a ket followed by a brat. I feel so weird saying that. But now, the reason this really works is because concepts of linear algebra, well, the finite dimensional vector space, it's just the laws of matrix multiplication. So it's not really as weird as it seems. But here's what applies to infinite bases too. So, but the thing is, here we have f by itself over here, and then we have f here. So what does that mean about this? That has to be 1. That has to be the identity. And sure enough, it is. That this, you think of this as an operator on a Hilbert space, that is the identity operator. And that's what you always have whenever you have an orthonormal basis. The identity operator is described by identity applied to any function f is just the same function f. And this summation is called a resolution of the identity. Now, it's the identity when you include all the basis members. One thing that's not really talked about here, but I just want to mention this aside, is that if you truncated this sum at a certain point, you would not have identity, but you'd have what's called a projection. That the basis functions, like from 1 up to n, let's say, those form a basis of what's called a subspace, an n-dimensional subspace of the overall Hilbert space. And this sum, truncated at n, would be a projection operator into it. So in fact, so I should mention that the analog to a finite dimensional vector space where vectors are in Rn. If I have an orthonormal basis for Rn, for example, if n equals 3, these are the vectors I, j, and k, or v1, v2, v3, then I have this relationship for any orthonormal basis Rn. This sum equals the identity matrix. So it's the same idea, just extended to an infinite basis for a Hilbert space. And I should mention that when you have two vectors in Rn or Cn, this, where you have a Hermitian transpose of u times v, that's called an inner product. It's really the dot product when you're talking about vectors in Rn or Cn. But notice here, it's the second vector that has the star. That's called an outer product. Now, the thing to be careful about, if you have two column vectors, the inner product or scalar product, dot product, in this case, they all mean the same thing. That's a number, it's a scalar. The outer product of column vectors is a matrix. Now, outer products tend not to be talked about in introductory linear algebra classes, but they still are. They can be quite useful. In this case, they're helpful for expressing projection operators or resolution of the identity. They're helpful for understanding how matrix multiplication works. So I feel like we're not talking about enough in such classes, but oh well, adult time. But yeah, you won't be seeing that through 26. Probably not. Oh, I've reached the end. I'm sorry, I didn't go that fast. I had no intention of reaching the end. Okay. I'll try not to do that again. Well, actually, I think the notes that I'll have in the future will not have as much in them. 7 pages per day seem like a lot. Okay. So, if I check on the schedule here. Okay. The first homework assignment is on section 5.1, which is what I've just finished covering. So you're now in a position to look at all those problems. It's not due for a while. Homework is always due on, let's see, I think it's always due on Thursdays. Yeah. So yeah, starting September 1st, and then every week thereafter for a while, like until fall break, there'll be one due. Okay, so what that means is that I think there should be time during each class, generally speaking, to address any questions on the homework. So so be sure to bring such questions with you. It's the best time to answer them where everybody can easily benefit. Are there any questions now? I know, it's late, y'all want to get out of here. I can't say I disagree. Except I don't get to go home yet. Every time there's always like post processing to do, get things on campus. But. Okay, then I will stop recording.